Good morning, everybody. Today we're going to be covering non-Mendelian crosses. This is our introduction to non-Mendelian crosses. We're going to finish this up next week. And so our objective today is to predict the results of crosses using scenarios involving non-Mendelian genetics. And so what is non-Mendelian genetics? And so this is going to be linked genes and sex-linked traits that do not follow the predicted ratios associated with Mendel's laws. And so what I want you to think about when we're dealing with non-Mendelian genetics is, what about all those exceptions for the rules, right? These are my exceptions for the rules. Not everything's easy and perfect when dealing with genes. And so this is where these gray areas kind of fall into play. And so genes that are adjacent and close to one another on the same chromosome and that are inherited together are known as linked genes. Traits that are determined by genes located on sex chromosomes are going to be known as sex-linked traits. And so we are going to talk about linked genes today and sex-linked traits. So linked genes are typically inherited together. This means that they're less likely to be separated during crossover in meiosis. And so if you see the picture, you're going to see gene A and gene B, that black and white band on that red chromosome. You're going to see those homologous chromosomes come together during meiosis 1, and crossing over is going to occur. But what do you notice? When that crossing over event finishes, gene A and gene B were not separated. They stay linked on that same chromosome. And so this is where I'm looking at right here. Map distance tells you how close together a pair of linked genes are. They are determined by how frequently a pair of genes participates in a single crossover event. Linked genes have a recombination frequency of less than 50%. And so if a pair of linked genes has a recombination frequency of 5%, that means that the genes are really close together on the chromosome, like gene A and gene B in my picture. These genes are considered to be 5 map units apart. Here's a different example. If a pair of linked genes has a recombination frequency of 30%, they're further apart. And so now you see gene A and gene B move further apart. Oops, I didn't mean to change the slide. Right here. So move further apart. Why they have that greater recombination frequency, and they're considered to be 30 map units apart. And so bottom line, map units can be used to determine the distance between genes on a chromosome. And so I'm going to be able to give you the recombination frequencies of different genes, and you're going to be able to place them in order like in this picture. And so let's do a practice problem together. And so what you see is genes A, B, C, and D are all located on the same chromosome. The recombination frequencies are as follows. So B and D are 14%, C and D 12%, A and D 6%, B and C 2%, A and B 8%. Your job is to find the order of genes on the chromosome. And so my first step is always to circle the biggest recombination frequency and the smallest, right? And so the green has the largest number, 14%, and then red has my smallest number at 2%. What I like to do is I like to find the biggest recombination frequency first, and then I know that's going to be the end, right? So because B and D have the biggest recombination frequency, that means they're going to be the furthest apart. So B and D are going to be the genes at the end. After that, I kind of find the smallest recombination frequency to fill in the order. And so I know B and C are close together because they're 2%. And then all I had to do was fill in A. And so the order is going to be gene B, C, A, D, respectively on this chromosome, due to the recombination frequencies provided. And so that's kind of my trick at figuring out these questions. Let's move on to sex-linked traits. Sex-linked traits are located on the sex chromosome. Sex chromosomes determine biological sex in animals. Sex chromosomes are non-homologous, that means they're not identical. And sex chromosomes can have different letter designations. Usually we see sex chromosomes with the letters X and Y. Biological females contain two X chromosomes, so XX, and biological males contain an X and a Y chromosome, so XY. The Y chromosome carries very little genetic information. When you look at a karyotype, you usually see the Y chromosome as a very, very small piece of chromosome or genetic material. Therefore, most sex-linked alleles are only carried on the X chromosome. Alleles are shown as a superscript on the X chromosome, for example, X superscript capital A or X superscript lowercase a. The way that I like to think about this, guys, is that the Y is wimpy, all right? Therefore, no alleles or no letters can be attached to it. And so I gave you possible genotype scenarios and how you would write those alleles out, whether you were our biological female or a biological male in the example. Something to note is that females are the only carriers or heterozygous combinations. Males, you're either homozygous dominant or homozygous recessive, right? You don't get an in-between. You don't get a mix because of that Y. And so females are the only carriers or heterozygotes. So here's a practice problem. In fruit flies, the gene for red eyes is X-linked dominant and white eyes is X-linked recessive. Cross a white eye female with a normal red-eyed male. Well, the first thing I did is make a key. My key looks a little bit different because now I have to make a key for both females and male. I can have X capital R for females with red eyes, X capital R, X lowercase r for females still with red eyes, they're just carriers or heterozygotes. I can have a female with white eyes, and I would show that as X lowercase r, X lowercase r. For males, we know that they're not going to have two X's. They're going to have an X and a Y. And so I can have X capital R Y for male with red eyes, or X lowercase r, Y with male with white eyes. After I create my key, I can find my parents. And so it says cross a white eye female, so I know that's going to be two lowercase letters, with a normal red-eyed male, and that's going to be one capital R with a Y, because males are X and Y. I go ahead and put my parents and set up on my Punnett square, one on top and one on the side, and I fill them in. Now, something to keep in mind, guys, is we're not only dealing with the trait of red or white eyes, right? We're also dealing with, is it a male or is it a female in this Punnett square, right? And so 100% of my female offsprings are going to have red eyes. 2 out of 2 squares, 2 out of the 4 squares are female, sorry. And out of those 2 squares, both squares show capital R, lowercase r, telling me that the female will be red. 2 out of the 4 squares are male. And so out of these 4 squares, out of these 2 squares that are male, both of them have lowercase r, y. So that's telling me that the males can only have white eyes. And so this is how you solve X-linked genetic problems. It is the same thing. The only difference is that you're putting the sex chromosome in front of it, and the allele is going to be a superscript. Now, the last thing you have to do is go to Teams, open up the assignment. You have 2 practice problems. One is of the linked genes, and one is of sex-linked traits. Go ahead and get that done. You highlight the right answer as usual, and then you're going to submit a picture of your work. Have a great day, have a great weekend, and be safe.